Ladies and gentlemen, I would like to present our contribution of a relatively wide range of authors from Slovak University of Technology Bratislava, from Cartograph Institute, and from University of Porto. The title is Influence of Additional Factors on the Integrity of Pipelines with Small Corrosion Defect. Probably this is the last time about the pipe, because in Europe it will be not gas and not oil. Motivation, this is all a joke, I hope. Short content of my presentation, motivation for this study, then define the integrity of pipeline with defect, what I mean, that appear the influence of additional factors, what are these additional factors and how it's necessary to calculate the influence, and then formulate some conclusions. In the beginning, design of majority of structures required the safety factor, like some factor against the plastic strain or plastic deformation, as we teach our students. In reality of operation, in industrial case of pipelines, this is not ideal, geometrically ideal bodies. Inaccuracy of roughness, producer say that are 2%, and 2%, the diameter, for example, 100 meter is not so small. Also the thickness is not accurate, not constant, and logical internal diameter a little bit change, a little bit deviate. Next additional problem is corrosion defects, small, large, and defect on the weld joint. This is reality in all the pipelines. This is the reality effect of the operational safety. That better expression of safety is the safety factor against the burst pressure, not against the elastic or plastic strain. It's documented these problems in operation of industrial cases, not ideal circle, problem with root of weld. Here is possible to see better. This is the one-axial axis of faces of two parts of pipe. Also is the problem, geometrical problem. The question: how assess the operational safety of such kind of pipelines? First possibility, the calculation of burst pressure. This is not so easy question, not so easy calculation. For example, this is one derivation of analytical solution for burst pressure in our university. Is based on the ideal geometry and the bilinear material model, which is based on the true stress-strain tensor diagram, and is expressed like a dependency of intensity of stress in the dependency of intensity of strain. Is considered the constant volume for this derivation. This way is relatively long. In the end, this is the destructive pressure or burst pressure when I fulfill the Huber-Mrs. Henke or von Mises criterion, or Treska criterion with a different expression. This constant A and B is somewhere, H is here. Deeply is commented this in this paper, and also will be presented in next papers. This derivation was based on the experimental study. These are the small specimen of pipe, 150 millimeters. Also in the real pipe, this is 500 millimeters. This is real destructive pressure. In our laboratories, this is a relatively dangerous experiment. Based on this experiment, was validate our was validate our criterion. But this is for criterion for ideal geometry. Real geometry with defects. Exists some standards which are very often to use in practice for a large dimension of defects. Is the ASME criterion, very well known. Also the D criterion. It's possible to see that these two criterions are more conservative than our criterion without the defects, because this criterion is based on the true strain stress. This is only conventional true stress. For small defects are considered Šulce or Kastner approach. Probably, for example, here are 2 points from this experimental burst pressure from our laboratories. this, sorry, a little bit back. This specimen for experimental testing included also the corrosion defects, that based on these experimental results, it's possible to formulate a methodology and approach how create the numerical simulation of this state, because real pipe, I once again repeat, have weld defect or corrosion defect, non-ideal geometry, and additional bending is another effect which is very dangerous. The solution will be a numerical simulation based on these experimental results. Many problems necessary to solve in this way. Define the elements type, mesh approach, model of material. I said that based on the true stress strain bilinear model. Also, criterion of destruction. What I mean? I very briefly comment. This is not automatically mean destructive pressure when in this corner overload stresses the ultimate strength, because a state around this is in elastic state, and it's not possible to propagate this plastic collapse. That better solution will be if this overcoming of ultimate stress around this area is also overcoming the yield stress. This is the situation that probably it's possible to propagate the plastic collapse to the burst pressure. Also depend of the dimension of this corrosion defects. This is relatively very large question. It's not time for here deeply to comment. Here is some example of simulation, elastic state. Now we start plastic state. Here are the corrosion defect, not corrosion defect of weld, yes, and overcome the ultimate stress, and around this is also plastic state. This is the burst pressure. Based on this simulation, it's possible to create influence diagrams of this additional factor. It's possible to see ideal pipe and increase the depth of defect. Defect is relatively small, 30 times 30 millimeters. Diameter of this calculation is half meter. Thickness, wall thickness is 10 millimeters. Material is X52. Here's the ideal pipe, only with defect increase the depth. Here's the, together with defect, also geometrical inaccuracy. Very strong influence have in the elastic state, this is logical, and then in the plastic state, in the stress formulation, a little bit small, but in the strain difference between, for example, this point is very large, logical. This influence on geometrical inaccuracies. Another, additional bending. This is the very dangerous things. It's possible to cause by subsoil deflection, subsoil sliding processes after raining, etc. Was prescribed like a deflection of this X at the distance from 2 to 10 meters. Possible to calculate also more. This is one example of results. This is the half meter dimension of pipe. This point is nominal stress without the corrosion and without the additional bending. Here it's possible to see addition in stress from depth of defect. Yes, this is over 50% because 10 millimeters is wall thickness. Then on the right side and left side is the addition of or increase of stresses, 4 meter stresses from the additional bending. This diagram is for over 4 meters deflection of axis of this pipe. Like example, it's possible to create many diagrams in this form. This is a different interpretation, for example, better readable. This is once again pipeline deflection. Here in this X, and here is the curve of increase of depth. This is no defect 2.4 millimeters, etc. It's possible to see here increase of stresses without the bending, and here increase with bending. Very strongly increase these stresses to the burst pressure. is the different diameter of pipe, 1.5 meter, for example. Also the same deflection of x from line. It's possible to express in the different form, in the form of safety factor of this pipe, like a ratio, yes, like a ratio between the burst pressure and operational pressure. This is the safety factor here from this data. Also possible to see here without the additional bending, here increase the depth, decrease from this point, decrease the safety factor when increase the depth, and increase the safety factor when increase the additional bending relatively strongly. And it's possible to create many diagrams, many nomograms like this. It's possible to say probably like a new standards for these industrial cases of pipelines with these additional factors. This is the evidence of reality. This is the real pipe, 0.5 meter, 8 millimeter thickness, real from 7.6 to 8.7 thickness, and weld defect inside in the root of the weld is until 30%. This is reality of all the pipe. That it's possible to conclude that real defect and operational condition are defined. Methodology of computational simulation was modified, was present based on the material model, true stress strain, burst pressure criterion. Influence of additional factors, additional bending was simulated and calculated, and these results are based on the experimental results. That's all from my side. Thank you for your time and attention.
So the